Okay. 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 Welcome, everybody. So I'm very happy to introduce Daniel Restrepo from Johns Hopkins. He will speak on Plateau's laws for surfaces of minimal capacity. Daniel.
Okay, thank you, Ovidio. I want to start thanking very much Ovidio, Daniela, and all the organizers. For me, it's an honor to be giving a talk here. I remember during the pandemic when this started and watching all the lectures and still learning about math was very encouraging for me. And it's I like to be at least one time from the other side of the thing, right? Like giving a lecture in this seminar. So everything that I'm going to say is a joint work or based on joint work with Francesco Maggi, Anna Skoborogatova, and Mike Novack. Okay, so what is the goal of this talk? The goal of this talk is to explain a family of variational models that you can see here that are basically versions of the Plateau problem or versions of the minimal capacity problem for surfaces. So let me stop for a moment here to explain what these models are. So essentially what we have is fundamentally a wire. So imagine for the rest of the talk that wire is basically a loop in R3. We have a density U that is defined in the complement of the wire. And since it is a density goes between 0 and 1. And what we want to do is to minimize the direct energy of this density U in the complement of the wire, plus maybe a potential that only depends on U. And then the novel feature of this very classical variational problem is that we are going to ask the level set of U equals 1 to satisfy a sort of boundary condition. So in this case, you have to think that U equals 1 is a surface that is spanning the wire. So very similar to Plateau problem. We're going to see it in a second. So we have this variational problem, and we have another version of the same variational problem with a volume constraint. So I'm interested in both of them. There is a little subtlety with the second, but essentially they are the same problem, more or less, plus technicalities. So what I want to do is to explain what is the meaning of this, what is the meaning of spanning the wire, because it plays a fundamental role even in the formulation of these problems. But this is the goal. Understand what do we get out of this? No surprise. No surprise. This condition U equals 1 will lead to a free boundary. So part of the problem is to understand the regularity of minimizers to this problem, but also the regularity of the set U equals 1. Okay. So let me start giving you a little bit of background of how these models, why are these models interesting, where they do appear. So as I said at the beginning, our benchmark is the Plateau problem. The classical Plateau problem is to find, given a wire that you see here, two Jordan curves, a surface that minimizes the area. So this is the classical Plateau problem, and here we have a very classical catenoid. Okay, now, what are Plateau's laws? So Plateau's laws, whose name are after the Belgian mathematician that introduced them, say that the mean curvature of the surface at points where the surface is smooth is 0. This is very classical. But life is not so easy for soft films. Soft films are not smooth everywhere, but the regularity at the points in which they are not completely regular the singularities are not that bad in the sense that as observed phenomenologically by Plateau, there are two types of singularities. Singularities that are known as Y points or like Y lines and T points. So these are here are two very concrete examples of Y lines and T points. So here we see that where the surface is regular, the mean curvature is 0. And where the surface is singular, either we have 3 surfaces meeting in 120 degrees, or we have 6 surfaces meeting along the skeleton of a tetrahedron. So this is everything. This is as bad as it can get. And this is what we're going to refer as Plateau's laws. Now, our starting point from a mathematical point of view is what is a possible mathematical model that is able to reproduce Plateau's laws. So there are several ways to reconstruct surfaces, minimal surfaces through sets of finite perimeter, through currents, through variables. All of them have certain features that are interesting, others have certain disadvantages. In our case, the right model is this idea of minimizing directly the Hausdorff measure with a boundary condition that is called the so-called homotopic spanning boundary condition, which was introduced by Jenny Harrison. And basically goes as follows. So we have our wire, we have the complement of our wire, and now we consider the fundamental group of the complement of the wire. So if this is not trivial, for instance, in the case of the catenoid, of the boundary of the catenoid, then we can take any loop, any homotopic class of this loop, and then start looking for surfaces S that are closed, or sets that are closed, such that these sets intersect all homotopic copies of this loop. So basically, when we ask all homotopic copies of this loop to intersect the surface, we're asking a sort of no-hole condition. So this is morally the idea. Here in this formulation, we can take as many loops as we want. I mean, as many loops, different homotopic classes are in the fundamental group, and different homotopic classes, of course, leads to different minimizers. To give you a simple idea of what this is, imagine the classical case of the catenoid, and imagine that we take two loops first. So we are considering gamma 1 and gamma 2, and all homotopic copies of them. So we have to intersect this, and this, and for gamma 2, all the copies. And a valid competitor in this case is the catenoid, since the catenoid intersect all of these loops. But now if we introduce, for instance, a third loop, gamma 3, then the catenoid will miss this loop. I mean, because we'll have that the catenoid won't see the loop, won't intersect it, and therefore the catenoid is excluded from the competition class, and we obtain a different minimizer that in this case will be the so-called Y catenoid. Okay, now, so this is the basic intuition of homotopic spanning models. Now, it is known that there exist minimizers for this problem. And moreover, minimizers actually recover Plateau's laws because minimizers satisfy the following property. If we take any minimizer and we deform it by a Lipschitz function, then this Lipschitz deformation is still a competitor, and therefore by minimality, we have that our limiting surface or our minimizer is a minimizer with respect to Lipschitz deformation, what is called in the literature Algren minimal. And Algren minimal surfaces actually satisfies Plateau's laws by several results of Algren and Taylor. So actually, this is a mathematical model that recovers Plateau's laws. So this from one hand. Now, on the other hand, the other ingredient of our notion of spanning that is not going to be exactly the spanning of Harrison is comes from the fact that subfilms are actually 3D objects. They have volume and they have thickness. And I'm going to talk a little bit more about this in a second, telling you why volume and thickness are important for the modeling of subfilms, at least saying what is captured by volume and thickness. But before doing that, I want to tell you a little bit about a model that was introduced by Maggi, Scardicchio, and Stewart, where they, instead of minimizing just a measure, they consider a class of objects that in this case are sets, open sets E, with certain volume B. And now what is being minimized is the perimeter of these sets. So now, so in simple words, instead of minimizing the area, instead of realizing solid films as surfaces, we're looking at solid films as boundaries of sets of finite perimeter. And this model here basically is an approximation to the Plateau problem, adding volume to the films. Now, the cartoon that we maybe have in mind for this problem is that basically, if we add volume to a minimal surfaces, we're going to thicken the minimal surface like this, adding a little bit of curvature. And as the volume goes to 0, these two leaves start converging until they clash into the limiting minimal surface. However, there is something that happens with this model that at first could be like as a drawback, but actually is very fundamental from both the geometric and also the physical point of view. And is when the limiting surface is a singular surface, for instance, this one. This is a cartoon in 2D of y lines. This is a y point, which is area minimizing, length minimizing. If we consider the model of Skoborogatova, Maggi, and Stewart, meaning that we start approximating this by open sets whose boundary is attached to the wire, then these open sets are covering the y point, but they start becoming narrower and narrower in certain parts, like here. And then in the end, and this part highlighted, the walls of the open set collapse and they gain multiplicity. So in a more precise sense, if we take a minimizing sequence of sets of finite perimeter with some positive volume B, if this B is small enough, then these sets are going to converge in the end to something more general than a set of finite perimeter. That would be a variafold. With multiplicity 2 in this collapse part, because we have the two faces of the set of finite perimeter clashing. We'll have an honest to God set of finite perimeter in the middle, and in this case with negative mean curvature. So this is, as I said before, something that from an intuitive point of view may seem as a drawback of the model because it's creating something that seems pathological. However, this kind of collapsing occurs for solid films. Okay, so as I said before, so the limiting object here in this model is not longer a set of finite perimeter. So a priori is just a variafold with bounded mean curvature, because here this set will have constant mean curvature, and this collapsed part will have zero mean curvature. So these things actually happen in real life because it's energetically convenient for solid films to allocate the volume, the soap with water nearby singularities, and become thin nearby it. And these kind of configurations of wedding around singularities, around the ideal singularities, are called in the literature Plateau borders. So this phenomenon is completely captured by the idea that nearby singularities, the area is more efficient to allocate area than nearby regular points. So that's why the singular points end up being wedded. But the main point that I want to stress about this model, which is natural because of these Plateau borders, is that the limiting object is not longer a closed set. I mean, in general, it's just, at least at this stage, is just a Borel set. And it has the structure of a variafold, but is not good enough to impose on it the spanning condition of Harrison. So bearing this in mind, in a work with Maggi and Novack, we introduce a different notion of spanning that agrees with the classical one, with the homotopic spanning condition for closed sets, but it can be generalized for more general sets, like for instance Borel sets. So what is the idea? In the idea of homotopic spanning, basically what is required is the surface to intersect loops. A condition that doesn't make sense, for instance, if the surface is defined almost HN almost everywhere, because if, for instance, we have a hole here, then the resulting thing will be equivalent to a surface, but we'll miss this loop. Then the basic intuition is to transfer intersection with a closed set by the notion of disconnectedness. So instead of considering a loop, which is negligible from the HN perspective, we thicken it to a tube. So we have a tube now. And instead of required, intersection with the tube is not enough, because that could be a possibility. It turns out that the right condition is the following. So we have the tube, the surface kind of disconnects the tube. It doesn't disconnect it, it only changes the topology of the tube. Now the tube will become a cylinder, right? But then if we add one slice, so any of the slices of the tube, then the union of the surface and the slice disconnects the tube into two connected components. So, and this is precisely this alternative definition of spanning. So given any loop in the homotopic class and any delta neighborhood of the tube is small enough so that the tube doesn't intersect the boundary, then we say that our surface is T-spanning if we take, for almost every slice of the tube, union the surface, this disconnects the tube into two connected components, and that's it. And this definition, at least in the case in which S is a closed set with finite Hausdorff measure, agree with the classical notion of spanning. Now, in the case in which S is just a Borel set.
Sorry, Daniel, but this is codimension one, right? These are
yes, this is codimension one. Yeah, we're only talking about codimension one.
Okay, thank you.
Okay, yeah, that's a good question. Thank you. So now, if we want to move from closed sets to Borel sets, then the classical notion of connectedness doesn't work immediately. I mean, it doesn't make sense even. But happily for us, there was already a notion of measure theoretical disconnectedness, essential disconnectedness or essential connectedness that was introduced in the work of Cagnetti, Colombo, De Filippis, and Maggi for the study of rigidity in symmetrization. And it's basically it basically changes the relatively open connected components, but sets of finite perimeter. And therefore, for instance, these tentacles doesn't belong to the reduced boundary of the corresponding things. And the same will happen if we just put holes. And therefore, this will be the essential connected components. So now the notion of T-spanning remains the same as I described before, but just changing disconnects by essentially disconnects. In theory, there are a couple of technicalities, but it's essentially that's the idea. Now, what are the advantages of this a little bit more complicated notion of spanning? That we can also use it to describe spanning for more irregular functions. Because remember that at the beginning I introduced these variational problems for continuous functions or for C1 functions, but C1 functions are not well suited for minimizing the Dirichlet energy. Then instead of working with C1 functions, we can work with H1, taking advantage that the precise representative is defined almost everywhere in Hn. Remember that we're working in Rn+1. Then for a Sobolev function, which says that U = 1 spans the wire, if for almost every superlevel set, which is a set of finite perimeter, thanks to the co-area formula, for almost almost every superlevel set, the epigraph U greater or equal than T is T spans gamma. And the key point of this formulation, from a technical point of view, is that it's closed with respect to the natural limits for Sobolev functions, meaning that if we have a sequence of Sobolev functions with L2 norm of the gradient bounded, and all of them is spanning the wire, T spanning the wire, then the weak limits in H1 also span the wire. So we have the closeness, the minimal closeness that we require in order to apply the direct method to find minimizers. Okay, so with all of this context, I can go back to the model and tells you like honestly what we got and how to understand them. So let's go back to model one. So model one is basically minimize the Dirichlet energy plus a potential. So what happens if we drop the potential for a moment? If we don't drop the potential, this is just minimizing the Dirichlet energy, asking the level set U equals 1 to expand the wire. And this corresponds to the classical minimal capacity problem for the minimal capacity problem for surfaces. And the model two, when we have a volume constraint, the motivation for this model is that, at least in the work with Maggi and Novack, if we take this potential to be the Allen-Cahn potential, the double wave potential, minimizers to this model as epsilon goes to 0 converge to the model of subfilms with volume. Okay, so remember that the capacity of a set is basically the infimum of the Dirichlet energy among functions that are greater or equal than 1 on the set and that are compactly supported. Then if the capacity of the wire is 0, we can see the surface of minimal capacity, basically as a surface that minimizes the capacity and spans the wire. So if we replace this in here, we'll get a double infimum, and this double infimum is nothing but the model that we had before. So this is truly the problem of surfaces of minimal capacity, which essentially is the main model upon which everything else will be understood. So all of these models with potential are basically perturbations of this one. So this is the only model that has to be understood to deduce regularity for solutions and also regularities for the free boundary. Okay, now the model of surface of minimal capacity is very ancient. I'm just going to make one reference that is traceable in the literature. There is this work of Griffith Evans, where he studied surfaces of minimal capacity in R2 and R3, very old work. And even Caffarelli has some work on this for minimal surfaces of minimal capacity attached to a knot. But the techniques in this case were a little bit different. They relied on multi-value harmonic functions, and they were able to identify branch sets using like techniques from complex analysis. I'm not going into that. But from this work of Evans, existence of solutions to the problem of minimal capacity is known. And also in my work with Maggi and Novack, we also were able to derive existence of solutions in the very particular case of Allen-Cahn for certain combinations of V's and epsilon. So this is what we have so far about existence. I want to remark this because another important result that I'm going to present by the end of the talk is related to existence for solutions. Okay, now let's talk a little bit about how solutions to this problem look like. So we have two models. One without volume potential. So let's set phi equals to the potential when we don't have a volume constraint. And when we have a volume constraint, it really doesn't matter that much because we can just combine the two potentials, put in a Lagrange multiplier. So in that regard, the volume potential from the local perspective of deriving regularity for this model is not playing a major role. It plays a major role for the existence, for compactness, but that's it. Okay, now, what are the criticality conditions for minimizers? So if we have a minimizer and we perturb the domain via a linear variation, if we do a domain variation, the spanning condition is not broken, is respected, and therefore we obtain the very classical inner variation. Now, on the other hand, if we consider an outer variation, meaning that we just perturb our solution upwards, this also respects the spanning condition because we are adding more set. We are increasing the epigraphs of U. U greater or equal than T is just increased by this kind of perturbation, and therefore we have this one-sided Euler-Lagrange equation. We get this differential inequality, and then if we consider these variations that are a little bit fancier, there is just T times H of U phi, where H is a function that is supported far from 1. So the variations also depend on U in this way. We're able to obtain this complementary condition, meaning that the equation is satisfied whenever U is not 1 and when U is 1 is 0. But this holds in the sense of distributions. So it's a delicate condition. This doesn't mean that this equation is being satisfied directly, the one here inside of the parentheses. It's saying that if we test this with a test function, an integral will get 0. Anyway, so these are the 3 criticality conditions for solutions to this problem. So we say that B is a critical point if it satisfies all of these 3 things. Then if we want to change this problem where the free boundary occurs when U equals 1 into a more natural setting, we can just consider B equals U minus 1, 1 minus U. And in this case, now the free boundary is on the 0 level set. And after a suitable choosing of the nonlinearity G, then we can rewrite everything. So this is now the key point to understand why regularity for this kind of problem is expected. So basically, we have that B satisfies this equation intuitively when B is greater than 0. Then if we ask G prime of 0 to be 0, then essentially this problem can be seen with this error here in L infinity as a lower order perturbation of B, of the Laplacian of B. So essentially the potentials are not contributing anything to the regularity of this problem, are just like a small perturbations of the same problem without potentials at all. And that's why I'm saying that all of these models for any range of potential that satisfy these conditions here are modeled upon the problem of surfaces of minimal capacity. Okay. Now, all right, then let me tell you a little bit about our results. So in a joint work with Mike Novack and Anna Skoborogatova, we proved that solutions to this problem are Lipschitz continuous with solutions and being minimizers. Minimizers to either model 1 or 2 and Lipschitz continuous with natural estimates. This is interior regularity. And this result is sharp because if we consider a harmonic function and we take phi being the absolute value of a harmonic function, this thing satisfies all criticality conditions. So it's subharmonic. It satisfies the inner variation because the inner variation is quadratic in the gradient, and if you take the gradient of this is plus minus the gradient of this. So if you have a function that is quadratic in the gradient of the function, it doesn't see the sign. So inner variation is satisfied and the outer variation is satisfied. And also whenever phi is not 0, we have the full equation. So Lipschitz regularity is sharp for this. And as I said before, this is only interior regularity. Something that is kind of funny is that even if this notion of homotopic spanning was devised to handle the boundary condition, there is no regularity result, but boundary regularity result for models with homotopic spanning. Now, what about the free boundary? So for the free boundary, we obtain the following. The free boundary of U, that is U equals 1, or in terms of B equals 0, can be decomposed into 2 parts, a singular part and a regular part. Now, the regular part is, sorry, this is a typo, is analytic. It's an analytic manifold. It's always analytic. And the singular part is yeah, and the singular part has codimension too, or has Hausdorff dimension at most n-1. And in particular, when in dimension n equals 2, then the singular set is basically given by points. And when the regular curves of the set b equals 0 meet, they meet in equal angles. Okay. I have to, so regarding this regularity for the free boundary, the regularity of the free boundary for this problem, and we'll see this in a moment when I start talking a little bit about the proofs. The regularity for this problem, at least for the free boundary, is very similar to the regularity of optimal partition and segregation problems. So in particular, after proving Lipschitz regularity for our model, almost the same techniques apply. And therefore, this regularity theorem here that of the decomposition of the free boundary is almost the same, or it could be even seen almost as a corollary of the work of Tavares and Terracini. So our main contribution for the regularity of this model is the regularity of U, because the regularity of the free boundary was more or less known, and the techniques can be easily adapted. All right. All right. Now, I want to say something about the proof. At least I want to highlight the main ideas in 2D. It is not surprising that since this notion of spanning, requiring the level set of V to decompose the tube into two connected components, kind of suggests that solutions to this problem introduce a version of optimal partitions, in the sense that if we look locally at if V is a minimizer, and if we look locally at B, then B is yielding an optimal partition for the ball, in the sense that if we change the boundary data, B still minimizes the Dirichlet energy as long as these connected components on the boundary are preserved. So in that sense, solutions to this problem are more or less the same as solutions to optimal partition problems, with the main caveat that the number of possible connected components, or the number of chambers here, is not prescribed. So the number of chambers can vary from ball to ball. Okay. Now, our last main theorem is existence. As I said before, existence for the minimal capacity problem was only known in 2 and 3D. And existence for the general model was only known in the case of Allen-Cahn, for some combinations of epsilon and volume. But in this case, thanks to our regularity results, we're able to obtain that under very natural assumptions on the potentials, like these things, there is always a minimizer. We have minimizers for all values of epsilon, for all values of V in Allen-Cahn, and for many more models. So in particular, for Allen-Cahn, that is the main application that we have in mind. F is this, and the volume potential is this one here. That was introduced in my work with Maggi and Novack. All right. Now, what about the proof? So what is the main idea to derive regularities for solutions of this problem? The main idea is inner variation plus the restricted outer variation are enough to conclude that the Algren frequency function is monotonic. And I mean, at least in the case in which F and B are 0. If F and B are not 0, based on the discussion that we had before, that all equations can now be written like this, with a function in L infinity, then this function won't be monotonic, but will be almost monotonic, which is enough for all purposes. Then in this regard, solutions to this problem basically behave like harmonic functions or two harmonic functions. The other key ingredient, and maybe the most important technical part in the derivation of the result, is this lower bound for the frequency function. So this lower bound, that is maybe the most important part, comes from the fact that if we are solving this kind of optimal partition problem, a lower bound in the frequency function just requires not having infinitely many connected components that are very thin. Not having a lower bound on the frequency function comes if we have a connected component that overtakes everything, and all the other components become very thin. And essentially, this is the kind of thing that that would destroy a lower bound on the frequency function. But thanks to minimality, we're able to rule out this case. Now, if this is true, if we have a lower bound on the frequency function and the frequency function is monotonic, is more or less a standard, show that solutions are actually Helder continuous. And if solutions are Helder continuous, we are in position to do blow-ups, rescaling by the height function, that is the denominator of the frequency. And these blow-ups will satisfy, again, all the criticality conditions. So for instance, in the planar case, blow-ups take this form. They are basically, for instance, when n equals 1, it's just a line. Is the regular blow-up is what you get when you are nearby a regular point. If n, sorry, n equals 2. If n equals 3, we obtain a triple junction, and so forth and so on. So since these are all the possible blow-ups, then Lipschitz regularity is just equivalent to show that the first blow-up that we can see is this one here, is the one with the line. And also notice that beyond the triple junction, also possible blow-ups for this problem could be quadruple junctions, quintuple junctions, and so on and so forth. So all of these guys actually appear as blow-ups. And in contrast with the Plateau's laws, these things are minimizers with respect to their boundary data. If you change the boundary data of these guys and you minimize the Dirichlet energy, if you minimize the Dirichlet energy with this boundary data, they will appear as minimizers if you are imposing the spanning condition. So you can't beat them all with the triple junction. One thing that is true, at least in the models of optimal partitions, is that the only singularities that appear generically are these. I mean, but we're not sure if the same happens for this model, probably. Now, in general, blow-ups are solutions to this problem, like are harmonic in their positivity set and also satisfy inner variation. For instance, if we go one dimension higher, if we go to any dimension, in the case in which, for instance, the frequency is 1, the nearby solutions to this problem will have only two connected components. And then if we take the function b and we reflect it to negative v, we will have a function that is smooth across and whose gradient is not 0, and will satisfy the PDE. So will be a harmonic function. And then thanks to the to the implicit function theorem, we can deduce that the level set nearby regular points is analytic. Now, as I said before, in 2D, the blow-ups are completely classified, are basically these two-value harmonic functions. When n is even, is actually comes from the absolute value of a harmonic function. When n is odd, for instance, in the triple junction, since it's not possible to make a coherent reflection, to reflect like in the case in which we have only two phases, then it's not the absolute value of a harmonic function, but it's the absolute value of a two-value harmonic function. But in any case, so Since in this case, since the blow-up take this form, actually we can deduce that in the limit, when these curves meet, that actually they have to meet with the same angles, and this is from where the same angle condition comes. All right. The one last thing that I want to say before finishing is, and this is the current state of my work with Anna and Mike. In 3D, now the criticality condition changes. Since blowups are homogeneous functions, the criticality condition in the space can be translated into a criticality condition on the sphere, and now blowups will be Dirichlet eigenvalues of the spherical Laplacian. So it boils down to understand what are the possible configurations of functions. Let me see if I have a picture here. Yes, is to understand the possible configurations where we have functions bi that satisfy this equation, the same lambda in each one of the connected components. When we reflect them, so when we have v and negative vj, they meet smoothly. So if you combine two of these regions, you obtain a new eigenfunction. And whenever they meet, they have to meet in equal angles. So basically, the classification of blowups in higher dimensions corresponds to understand what are the possible combinations of this. And I think this is it. Yes, thank you.
Okay, thank you, Daniel. Let's see, are there questions, comments?
Can I ask a question?
Yeah, go ahead.
Yeah, so in your analysis, it's so I was curious about at the beginning what you said, that you can only observe Y shapes and the other with 6 junctions or something, right? You show us these pictures of so it was either, right? I mean, Y shape or the other shape.
The one of subfilms?
Yeah. So in your analysis, you get like any kind of partition is possible, right? Whereas
Oh, yes, yes, yes.
So how does that? Yeah.
So for the minimal capacity problem, there are other configurations like different from the Plateau's laws. So when the type since the title of the talk says Plateau's laws for surfaces of minimal capacity, is a little bit misleading, because this is not implying that the Plateau's laws apply to surfaces of minimal capacity, saying that there are different laws for the surfaces of minimal capacity. At least the law in 2D is that when you have lines of minimal capacity, they have to meet in equal angles. That doesn't have to be triple junction, could be any order of junction, but they have to be in equal angles.
Okay, so the law you impose is different between this model and over your model. Is that what you're?
Yeah. The law that is obtained a posteriori that is found for minimizers is different. Is weaker than the Plateau law.
Okay. Okay. Yeah. So actually the picture I was referring to was this picture. The real picture with wires.
Yeah, I was going back, but was at the very beginning.
Yeah, that one. That one.
Taking it too long.
Yeah. Okay. Okay. Thank you.
Okay, let's see. Other questions? Let's say I have a question. So if we go in 3D, are there any, I mean, do you conjecture that what you get are just the solid, like the
Platonic solids?
Icosahedron, yeah, Platonic solid plus things from 2D extended by one variable height? Would this be like a reasonable conjecture? Or
so in Yeah, I've been thinking a lot about it. So in 3D, you get all harmonic polynomials. So you get the harmonic polynomials, which will be more or less trivial in the sense, because you can use harmonic polynomials to split the sphere. So I have some examples here. So there is this result of Hans Lewy that says that for any odd degree, for any odd number, there exists a harmonic polynomial of odd degree that splits the sphere into two connected components. This one. So this is an example of a degree 3 thing. But then in this case, the frequency has to be an odd number. So it's very large, and you can isolate them. You can, so there are like pathological cases. You can extract them, put them apart. Then you have the cylindrical cones, as you said, like the Y. You have also like the N junction cylindrical. And then you have the nets. But now, so there are two problems. One of them is these curves on the sphere, they don't have to be geodesic. And there are numerical experiments that show that they don't have to be geodesic. When I say numerical experiments, I mean in spectral optimal partitions. They don't have to be geodesics. There are examples in which they curve a little bit. But something that is true, and is if you take the geodesic nets with triple junctions, thanks to the you obtain platonic solids, right? You get the dodecahedron, you obtain the tetrahedron. Those are minimizers. Sorry, those are cones, valid cones. You can show that they satisfy all the possibilities. I don't know if those are all. I'm not sure.
Okay. How about maybe like boundary regularity for the free boundary? Probably is right. Like the way I understand it, you start with the Y. Unlike, let's say, with the surfaces of minimal capacity. Like how regular are they when they touch the boundary, or?
No, I don't know. We haven't thought about it yet.
Mm-hmm.
I think, it will be the case of like trying to use again the Eigen frequency, the frequency function at the boundary level. And then I think that at least in 2D, you'll also get a sort of like a equal angle condition. It's a little bit different because equal angles at the boundary is slightly different because you get like one of these 2D blow-ups. Like let's say that you have one of these, and then you cut it by a plane, and then at the boundary you could have something like this, like this three. But I don't know what is the right regularity. I think I expect to be Lipschitz as again Lipschitz up to the boundary, but I'm not sure.
Okay, so let's see. Are there other questions? Okay, if not, let's thank Daniel again for a very nice talk.